Today we are going to see regularization techniques. First, let us see what is overfitting and generalization. Then we will see regularization techniques to control overfitting. In our linear regression example, we trained the model by minimizing the training error. But we really care about the test error. The process of adjusting a model to get best performance possible on the training data is called as optimization. The ability to perform well on previously unobserved inputs, means test set, is called as generalization. At the beginning of the training, optimization and generalization are correlated. See here, up to this point, both training error and test error are decreasing. Both are decreasing, so both are correlated. These two factors will determine how well a machine learning algorithm will perform. One, make the training error small. This training error should be small, and the gap between this train error and test error should be small. First training error should be small, then gap between this train and test error should be small. If you have high loss on training and test data, then your model is said to be underfit. See here, hyperplane constructed by this model is like this red line. Here, all the stars above the line and the stars below the line are wrongly classified. Means this constructed model did not capture all relevant patterns within this data. There is scope for improvement. For this model, this training and test errors are high. Somewhere here, you need to decrease them. Previous model does not fit well, so need to increase training. But after certain number of epochs, generalization stops improving and began to degrade. In previous model, we have high train and test errors, so we need to train the model for more number of epochs. So after certain number of epochs, this train error is decreasing, but this test error stops decreasing and it is increasing. Means this model is learning patterns that are specific to training data but irrelevant when it comes to new data. Means it will not perform well on the unseen data. So we can say that this model is starting to overfit. We can control whether a model is more likely to overfit or underfit by altering its capacity. Models with low capacity may struggle to fit the training set like this. Models with high capacity may overfit by memorizing properties of the training data that do not serve them well on the test data. This kind of models. We need to choose optimum model which serves well on both training and test data like this, compared to this model which has less accuracy on training set but it will generalize better. It will perform well on the unseen inputs. To prevent overfitting, best solution is more training data. The dataset should cover the full range of inputs that the model is expected to handle. A model trained on more complete training data will naturally generalize better, but getting more data may not be possible in many cases. Even if it is possible, it might cost more money. The next solution is to reduce the size of our network. However, larger networks are more powerful than smaller networks, so this option is rarely adopted. Fortunately, there are other techniques which can reduce overfitting and improve generalization performance even when we have fixed network and fixed training data. These techniques are called as regularization techniques. Regularization places a constraint on the quantity and type of information your model can store. If a network can only afford to memorize a small number of patterns, the optimization process will force it to focus on most prominent patterns, which have better chances of generalizing well. All these are the most commonly used regularization techniques: weight regularization, L1 and L2 regularizations, dropout, data augmentation, early stopping, and batch normalization. Let's see the L2 regularization. L2 regularization, which is based on L2 norm. In L2 regularization, we add extra term to the cost function. This is the cost function. We will add this extra term. This term is called as regularization term. If you write this original unregularized cost function as C0, then regularized cost function can be written like this: C0 plus this regularization term. Intuitively, the effect of regularization may make network prefers to learn small weights, all other things being equal. Regularization can be viewed as way of compromising between finding small weights and minimizing the original cost function. The relative importance of the two elements depends on the value of lambda. When lambda is small, we prefer to minimize the original cost function. We try to minimize this cost function. But when lambda is large, we prefer small weights. Let's see the effect of regularization. This is our cost function. In the training, we need partial derivatives of cost function with respect to parameters. The partial derivative of cost function with respect to weight W is this one. This dou C naught by dou W and dou C naught by dou V can be computed by using backpropagation. Add this lambda by NW to the partial derivative of all weight terms. Then learning rule for weights becomes like this. New weight W dash will be W minus alpha times dou C naught by dou W minus alpha times lambda W by N. We can rewrite like this. This is same as usual gradient descent learning rule, except we are rescaling W by factor 1 minus alpha lambda by N. This L2 regularization called as weight decay since it makes the weight smaller. Let's see L1 regularization. In L1 regularization, we add L1 norm to the unregularized cost function. L1 norm means sum of absolute values of weights. So regularized cost function C would be C naught plus this regularization term. Learning rule would be this one. Here the partial derivative of cost function C with respect to W would be this one. If sign of W is positive, then new weight W dash would be this one. If the sign of W is negative, then new weight W dash would be this one. Both L1 and L2 regularization penalizes large weights, but the way weights shrink is different. In L1 regularization, the weights shrink by a constant amount towards 0. But in L2 regularization, the weights shrink by an amount which is proportional to W. You can see here. If particular weight has larger magnitude, L1 regularization shrinks the weight much less than L2 regularization. But when weight magnitude is small, L1 regularization shrinks the weight much more than L2 regularization. Net result is L1 regularization tends to concentrate the weights of the network in relatively small number of high important connections, while other weights are driven towards 0. Does this L1 and L2 regularization really reduce overfitting? Both L1 and L2 regularizations keep weights smaller. Smaller weights prevents excessive fluctuations of the coefficients like this green smooth curve. So overfitting will be reduced. If you have larger coefficients, then curve would be something like this. If some weights are 0 or closer to 0, some neurons in the network does not contribute much in the calculation of the outputs. Suppose the weights which are connected to this neuron which are smaller or 0, then net output at this neuron becomes 0, so which will not contribute in the output. So some of the neurons within the network does not contribute within the output, so your network will become sparse, all these neurons not contributing much in the output. So your final network would be something like this with these neurons. So the network becomes sparse. Instead of this complex curve, this sparse network will form this kind of simple curve, this blue curve. Let's see the dropout regularization. Dropout does not modify the cost function. Instead, it modifies the network itself. Let's see how it works. Suppose we are trying to train a neural network without dropout. Let's assume input is X and output is Y. This might be vector. We would train by forward propagating input X through this network and then back propagating to determine the contribution to the gradient. But with dropout, this process will be modified. We temporarily delete half of the neurons within the hidden layers while leaving this input and output neurons untouched. After doing this, our network would be something like this. The input X will be forward propagated through this modified network and then backpropagate the result also through this modified network. Weights will be updated. Same process will be repeated with different set of dropout neurons. In the next iteration, you might drop this first and third and this last neuron, and we will update the weights with this modified network. By repeating this process over and over, our network will learn set of weights. Of course, those weights will have been learnt under condition in which half of the hidden neurons were dropped out. When we drop out different set of neurons, it's like we are training different neural networks. So the dropout procedure is like averaging the effects of a very large number of different neural networks. The different networks will overfit in different ways, so the net effect of dropout will be reduced overfitting. Let's see another technique, data augmentation. We already discussed if we increase more complete training data, it will reduce overfitting, but it is difficult to get more data in some cases. In these situations, we can artificially generate more training data. Data augmentation is the technique which will increase training data by adding slightly modified copies of already existing data. It acts as a regularizer. For images, flipping, color modification, cropping, rotation, noise injection, etc. are used to generate artificial data. If dataset is too small, we can use generative adversarial networks to create new synthetic images for data augmentation. Let's see early stopping. To improve the performance of model, if we increase more number of epochs, initially both optimization and generalization errors will be decreased, means training and test errors will be decreased. But after certain number of epochs, this generalization stops improving, means test error will not decrease, even it might increase, means model is learning patterns that are specific to training data, so training error is decreasing. But when it comes to testing data, these patterns are irrelevant, so this test error will be increased. Early stopping rules provide guidance as to how many iterations can be run before the model begins to overfit. Means we have to stop at some point where this model starts overfitting. Stop training when monitored metric has stopped improving. Model.fit training loop will check at end of every epoch whether the loss is no longer decreasing. Once it is found no longer decreasing, training will be terminated.